Hello everyone, we're here with another video. So the last time, to quickly recap on what we've done the last time. So we went through Pascal's triangle. We've also seen basically Pascal's triangle was important if we needed to know the number of combinations given a specific number of sets. Say for example, I have a set of 5 elements and you just want to know the number of combinations when we take 2 elements out of the 4 or 5 elements. So we use the factorial notation, and the notation is as we are seeing here. This is how it looks like, and this is how it's written in the literature. So n capital C with subscriptive the number of elements you need to take, the subset, basically the number of combinations. We were also acquainted with what the union is and the intersection. So we know the union is basically the or, and the intersection is the and. And Venn diagrams are the best way to visualize these sets and then easily extract the unions and the intersections. The subtraction is basically saying you eliminate the elements from a specific set. What else? We've also seen the complement. So complement anything that's not in the given set. We've also so there was this summary that we discovered, which was pretty. Where was it? Yeah, I think it's this one. Yeah, the summary here was pretty nice. I mean, it included most of the terminologies we were introduced to, so we will be sticking to these terms. And so, for example, this is the intersection, and this is the complement, subtraction. Let's go back to the notes just to quickly recap and then revisit the important bits. One thing so the real numbers include fractional and irrational numbers. So real numbers basically encompass everything, be it floats, integer, positives, and so on. So the other representation we were acquainted with is the square brackets. So when you talk about square brackets of an element for a given set, it means that that element is included in the set. A round bracket says it doesn't include. So if we try to represent this in a line number format, so we have, say, a set of the numbers greater than 0 but less than or equal 20. So in this case, the 0 is not included, which is represented by an empty circle, and 20 in this case is included in the elements, in the number, and in the set. So it's a filled circle. Yeah, so this is the representation, and you would have a square bracket for the inclusive part, and the exclusion you would just go with the brace. Yeah, so with the round bracket as we see here. So these are two different examples, and basically that was it. So going back to the summary page, yeah, we tried to look into so the book has some weird terminologies, but they all serve the same purpose. So if you take a look at the summary here, so when we had the summary, yeah, it's this one. So there is this symmetric difference of sets, and then there's the complement, and then some other, yeah, so there is Morgan's law, De Morgan's law, in which where you have a union and the intersection, when they are both complemented, the union becomes an intersection, and the intersection becomes a union. And the other mathematical formulas introduced here, say, for example, when you have a union of multiple elements, and then you subtract in between, and you do the whole magic of association. And so when you apply Cartesian products, association, distribution, association, and cumulation. So commutative law, it means basically A union B is the same as B union A, and the intersection applies the same. Associative laws is like when you have, in this case, A union B, it's the same, A union B, union C is the same as B union C union A, or whatever. So the union really doesn't matter. The union here in this case is just moving the brackets around, doesn't make a difference. The same applies for the intersection. However, for distributive laws, things vary a little bit. In this case, it's like you multiply in these brackets and the circular brackets. So A union B intersection with A union C, and then A intersection with B union A intersection with C. So these laws So this mathematical formulas for sets is really what is the deal behind all of these, is that instead of you going and proving each one of them, they've summarized the list here. So for example, when you have a set A subtracted from the collection of B union C, or a set of B resulting from B union C. So you could simply go, instead of you visualizing it, you could say, for example, you have a set of 1,000 elements. Now you can't really write down all of the elements and combinations possible. So in this case, you would just go with A, you subtract A from B, and then, so this is the, what do you call it, the distributive law. So it's similar to the distributive law. So A is minus subtracted from B, and then the union becomes an intersection, and then A minus C, just like that. Okay. So these laws, now you could prove these using the same approach done here. So for example, you have A, B, and C, and D. So the list of elements in A, and list of elements in B, and list of we've done this in the previous video, so I really I'm not going through all of it. Now I'm just trying to quickly recall what we've done. So the union of A union B union C is like all the elements together, eliminating the duplicates, and then A intersection of B, and then B intersection of C, and then C intersection of D. So basically we've listed all the possible outcomes from the intersections, because the reason why we're opting for the intersection is because we want to achieve this formula here, this one here, because we know the number of elements in A union B, so n here means the number of elements. So in order for us to get the precise number of elements and remove the duplicates mathematically without using the visuals like Venn diagram and all, and without doing it manually, again, imagine this is 1,000, this element has this set has 1,000 elements in it, and B is the same. You won't really finish until maybe next year. But my point is, the number of elements in A union B. You need to get the number of elements in A and the number of elements in B, add them together, and then eliminate the duplicates. How would you do that? Is from the duplicates means the intersection. The intersection would yield, would basically eliminate any duplicates that can happen. So this is really important for future reference, for future examples too. So the intersection would eliminate any possible duplicates for you. So that's why we subtract the intersection here from the number of elements. And that's how we get the number of elements in A union B. Now, this gets a bit complicated when you add another element to the mix. So instead of you working with 2 sets, let's say you're working with three sets. So the number of elements in A union B union C is the number of elements in A, then plus the number of elements in B, plus the number of elements in C, minus all the duplicates that could happen in the as a result of the intersection between A and B, B and C, and A and C. So that's correct. So A intersecting with B minus B intersecting with C minus A intersecting with C. Now there's something else being added here. And then you add the intersection of all of these together. I'm not sure why this is the case here, but I'm sure there is a reason. So let's assume that there is a reason. So, but the general notion is that the more you grow, the more you add and subtract. So you have four sets here, each has its own set of elements. So n number of elements in A plus the number of elements in B plus the number of elements in C plus the number of elements in D, and then you subtract A intersecting with B, B with C, C with D, and then A with D, and then B with D, and then A with C. Yeah, A with C, and then you add the intersection of all of these together. I'm not really sure what's the deal here. I'm not sure what the formula is behind. What's the formula here is about, because as you can see, he added all the 3 elements together, but then subtracted the sets, the intersection of the 4 sets, while in the previous example he added instead of subtracting. Why? Oh my god, this is confusing. What's he doing? Therefore left hand side equals right hand side. Alright, let's just the Cartesian product. Yeah, so the Cartesian product is basically you create a mix of 2 points, say A is 1, 2, 3 and B is A and B, then each element would correspond to its so 1 with A and then 1 with B, and then 2 with A and then 2 with B, 3 with A and 3 with B. So that's the Cartesian. This would be mostly useful when you're drawing graphs. So this would be quite handy because you'll have a combination, a set of elements. But the confusing part is this is interesting. This is a good summary, but we have to know the source as why to this happened. As to why has this happened, let's explore more. Alright, so with the book, back to the book. No, I mean, getting the unions and all, it's fine. Getting the end result is fine. But the problem is, now from the summary list here, is the number of elements, obtaining the number of elements in a given set. So when you go union of 4 sets together, you would want to know the number of elements that should exist, like more like a way to validate that your work is correct. So when you do the union, you know that, you just merge all the elements together and then remove all the duplicates. That's totally fine, but you want to know the number that you should have. As the number of elements, as the number of sets grow, that's when things get complicated. And we should expect the elements to grow because you will be working with large amounts of data. So in this case, what we should do is we really can't know. You see, in this example, the number of elements in a given set are basically, the maximum is like what, 6, and then the minimum is like 5. So it's a manageable number, but imagine the set has like 100 elements, and just imagine you having to write down all the possible outcomes. It doesn't really make sense. But at the same time, there is no clear approach as to why this happened. Well, I just have to check with Google then. So, obtaining the list of elements. This is a collection. To list elements. Let's check out Stack Exchange. If A, so this is the Cartesian product of set A, M and A belongs to A, M is greater than N. That's the Cartesian product. So in this case, you will have to have 1, 1 with 1, 2, 1, 3, 1, 4, and so on. Each pair in B, you have to take in M in 1, 2, 3, and N in 1, 2, 3, 4, 5. Nope, this is not what we're looking for. So we know what the sets are. 5 belongs to D, as A is an element of D, yeah. 2 is not an element. This is the notation. So such that, yeah, so the x says that x is an integer between 5 and 7 inclusive. So 5, so x is greater or equal to 5 but less or equal to 7. And then we have the empty set, which is part of the reset. That's totally fine. Okay, so these are the subsets, universal sets of, yeah, the union is totally fine. Okay, union is totally fine here. And then the associative rule applies here. So A union B union C is the same as A union B union C, the same as B union A union C. So changing the sets about doesn't change the result. This is a reliable set, no matter what set you choose. If, assuming it's the same number of elements regardless of the order, the result would always be the same. Now, the complement, A complement union B union C. So A complement means, so we have A 1, 2, 3, 4 and B 2, 4, 6, 8. What's the universal set? So the universal set is 1 to 10. Okay, so A complement means you have 6, 8, 7, 8, 9, 10. That's what the A complement is. Okay, and then because the A stops at 4, then the A complement starts at 5. So 5, 6, 7, 8, 9, 10. That is correct. Alright, where we are. Yeah, the empty set. When you have the union with an empty set, you'll always have the same set. But if it's an intersection, then it's always an empty set. Yeah, because remember, it's an OR. An empty set or a list of an empty set and the set, then it's always the empty set that is intersecting with the original set. And an empty list is a subset of A. Notice here that it's a proper subset. It's not just a normal subset, it's a proper subset. The union with A complement is the universal list. Yeah, of course, that's obvious. I think we should write down this. This is a really good summary. It's way better than the previous one. Disjoint sets. We've reached the bottom. Now, where did we check the number? Numbers. No, it really suffice, but this is a really good summary. We should keep it. And in union of sets, yeah. Number of elements in union set theory. So in this case, set A contains 35 elements, set B contains 22 elements. If there are 40 elements in A union B, then how many elements are in A intersecting? Oh man, this is what we're looking for. What a nice Paint website. What is this? Okay, so using the formula for cardinal number of the union of two sets to solve the problem. Alright, let's see what the answer is. Okay, so A union B is A plus. So this is the rule. This is the golden rule, yeah? Okay, so where the notation X is used for the number of elements of the finite set of X. Okay, according to this formula, A intersecting with B. Yeah, so you just play around with this. So instead of this, so A union B would equal A. So A intersecting would be A. No. Yeah, that is correct. No, so this is the golden rule. This is very important to know. Now, if you want to get A intersecting with B, then if you throw this to the other side, that becomes positive, and this becomes negative, and this is where you end up with A plus B minus the union of both A and B. This is interesting. I should keep this open. Okay, so this is the golden rule. So the cardinal number of the union of the finite set is set A contains, and there are, okay, the cardinal number. This is quite interesting to me. So just have this recorded. So let's copy this example. and then the end result would be, this would yield this result. So this is the answer. There we are. Just copy this here, just in case. All right. That's that. Yeah, this is interesting. Math could use. Yeah, see, to represent relationships between sets. Let's look at example below. Using the Venn diagram is quite simple and straightforward. We don't want to use that for now. We've seen it's quite easy to use when you have small number of elements in a given set, but the moment numbers start to grow, then you'll have a really hard time. So this is not what we're looking for. How many elements are in a union set? I should have noticed this before jumping into anything else. That's, oh, how many elements? So this is a book. Apparently the rule of the union is what's crushing everyone else. So that's basically, that's the golden rule. The union. The union of sets. The union is a set. Let's check Wikipedia. Should check Wikipedia. Alright, I think we're done. Right, back, just had to finish some stuff. Anyways, so on with the unions. So what I plan to do now is, you can see that the union is basically associative in the sense that if you have A union B union C, you can go like A B union C, solve for this, the result you would union it with A. So I'm guessing that in this case, this means that instead of us solving this whole thing this way, in this approach, we could just break it down to smaller chunks and solve each set or each component together. So in this case, A union B, solve for N union B, and then solve for B union C, and then solve for the results of both. I'm guessing this is how I would do it, and I'll give this a shot using this and see if this would yield the number of elements. So, and see if this would yield the intersection is 1, would yield 9. Well, it should yield 9 anyways. Should do an exercise on this. Should do some exercises on this. So I think okay. Basically, the most important, the golden rule here is that the association works, and we know about this. The complement, we know about that too. The number of elements is if you want to get the number of elements, we have to use the golden rule again, which is this rule here. Bring things down and solve accordingly. We have this summary here in which it summarizes a lot of things to us. Let me copy this. This is very important. You should add it to the list of summaries here, which is we've had this linked somewhere. Where are the links? Yeah, summary of sets. Should have this dropped below. Okay. So this joint set is basically the intersection would yield an empty set. The intersection is an empty set. This is disjoint. Let's go back to the textbook like really quickly and the symmetric difference. I'm not sure what the symmetric is anyway, so we'll leave this for the next session. But the Cartesian product is a coordinate of x and y. Okay. Exponents. You know, we could also work on this, proving these rules. But let's see what the symmetric difference is. What the symmetric difference in sets. See if this summary has anything about symmetry. Nope, nothing on there. Symmetric. Is a type of symmetric difference. Okay, this is what we're looking for. In mathematics, the symmetric difference, also known as the disjunctive union of two sets. Oh, so basically this is the symmetric difference. So you have the union, but excluding the intersection. Interesting. Let's see what the summary has. So for the symmetric, which is a rectangle symbol, yeah, so A minus B union B minus A. So basically, why not just have a union B and then subtract the intersection? Why not do that? So we have A minus B. So this is the example 0, 4, 0, 2, 4, 6, 10, 1, 2, 4, 5. So A minus B is basically 0, then 6, 8, and 10. And then B minus A is basically 1, 3, and 5. B minus A. You eliminate all the elements in A that exist in B. So it's 1, 3, 5 is what's left. So the union of these two is 0, 1, 0, 1, 3, 0, 1, 3, 5, 6, 8, 10. Now what if we did this instead of A minus B union B minus A? What if we do the union minus the intersection? Yeah, but how would you go about the intersection? You don't have a formula for the intersection. Okay, so let's go for the intersection now. The intersection is 2, 4, 2 and 4. So it's 2 and 4, that's the intersection. So the union is all these elements minus 2 and 4. So we will be left with, so if we have the number of elements here, just go in It's 0, 1, 2, 3, 4, 5, 6, 8, and 10. 8 and 10. There's no 9 and there's no 7. So the intersection is 6 and 8. If you go like, if you intersect beta with A, so 2 is there, 4, and that's about it. If we subtract this from this, we will be left with 6 and 8, we'll be left with this. 0, 1, so there's no 2. Oh, sorry, it's my bad. So the intersection is actually 2 and 4. Intersection is 2 and 4. So this minus this, so we eliminate 2 and we eliminate the 4. So 1, 3, 5, 6. This actually works. This is nice. Okay, so why do we have to go for? So in this case, what it's done is A minus B union B minus A. So what they've done is A, so let's go for this, A minus B. A minus B will be left with this portion, union B minus A will be left with this portion. Or you could go like the union minus the intersection. Yeah, so it should work. Yeah. Now what if it's the 3? So if it's the 3, then you would go like the union of all of these minus the intersection. Oh no. What? So there's this intersection here. X square. Both are relative complements. You have to study this separately, so it seems there's a lot to the difference is the disjunctive union of two sets is the set of elements which are in either of the sets and not in their intersection. Okay, so in this case A and B, but this is intersecting here. Why is it red? Oh my god, this is so good. Anyways, I think we should stop here and finish later. Bye.